A volcano awakens in Iceland. A mountain erupts, belching millions of tons of ash into the sky. Airlines soon feel the effect. 100,000 flights are canceled. Around 10 million passengers stranded.
Chaos, aircraft grounded, airlines going out of business.
Had an enormous impact for aviation, brought Europe to a standstill.
The impact quickly spreads. Freight movement around the globe is crippled, costing the world's already fragile economy billions of dollars. And now, scientists are discovering volcanoes in Iceland that can dwarf this eruption of ash in 2010. Volcanoes that produce killer clouds of sulfuric acid. And most alarming of all, a giant ice-covered volcano that's overdue to erupt and that could impact the entire planet.
Nowadays, we are very vulnerable to volcanic eruptions.
It's not a matter of if, it's when.
Volcanoes can be considered a ticking time bomb.
I would predict that we would see death tolls running into the hundreds of thousands.
How threatening could the next eruption from Iceland be? Doomsday volcanoes, right now on Nova.
Major funding for NOVA is provided by the following. The David H. Koch Fund for Science, supporting NOVA and promoting public understanding of science. And by the Corporation for Public Broadcasting. And by contributions to your PBS station from viewers like you. Thank you. Additional funding is provided by Millicent Bell through the Millicent and Eugene Bell Foundation.
Reykjavik, the world's most northern capital city. Home to most of Iceland's 320,000 inhabitants. Over 1,000 years ago, the Vikings settled this frozen land. Today, tourists flock here to marvel at Iceland's explosive geysers and boiling pools. But this abundant thermal energy has a darker side. Its volcanic threat. In 2010, the volcano Eyjafjallajökull, nicknamed Eyja, explodes into life. The eruption lasts for over 2 months. Icelanders head for shelter as the ash rains down. But Eyja's effects are soon felt globally when the ash cloud spreads into the busy routes of transatlantic aircraft. Airports around the globe are gridlocked as thousands of flights are canceled. But scientists are concerned much worse could come from Iceland.
I think we dodged a bullet with the 2010 eruption. In the future, there are going to be eruptions in Iceland much bigger than the 2010 event.
These scientists are uncovering the devastating effects of past volcanic eruptions and trying to predict how widespread the deadly consequences of the next eruption could be. Thor Thordarson is a volcanologist. He knows Iceland's volcanic threat well, having spent almost 30 years mapping its complex geology.
The amazing thing about Iceland is that it has 30 active volcanic systems.
Iceland is about the size of Kentucky. With so many live volcanoes in such a small area, it's one of the most volcanically active places on Earth. But while Ea sleeps again, 3 nearby volcanoes are cause for concern.
Since the eruption at Eyjafjallajökull in 2010, we are keeping a close eye on 3 volcanoes, the Hekla volcano, Katla and Laki.
Ea's volcanic neighbors, Hekla, Katla, and Laki, are clustered in a zone of intense volcanism in the south of the island. Each has a distinct personality. Laki, a fissure volcano that tears across the landscape for 17 miles. She last erupted in 1783, wiping out 1/5 of Iceland's population. Hekla, a menacing peak almost 5,000 feet high. Historically, she has erupted violently without warning, belching vast amounts of ash. And Katla, a giant volcano 18 miles across, hidden under 2,000 feet of ice. Katla is decades overdue for an eruption. She's currently rumbling, so volcanologists are most worried about her. So why does Iceland have so many threatening volcanoes packed into such a small area? It's a result of its unique location. Iceland lies in the North Atlantic, between North America, Greenland, and Europe. Here, 2 of the Earth's crustal plates are being pulled apart, and Iceland straddles their boundaries. Below is a hot spot, a huge upwelling of hot rock from deep within the Earth. As the rock rises, it produces magma. The magma forces through cracks in the crust until it erupts at the surface, forming active volcanoes.
One of the reasons why it is difficult to predict volcanic eruptions is that we try to predict behavior of something that we can't see. We can't see the magma that actually is the source of these events.
Above ground, Ea, Laki, Hekla, and Katla appear to be separate volcanoes. But some scientists are starting to wonder if they might be linked underground, and that Ea's recent eruption could have disturbed one of its neighbors. Now, there's an astonishing place that helps reveal how volcanoes are linked.
It is exciting to be here. It's quite unique to be able to go down into the crater.
These geologists are about to take an incredible journey into the heart of a volcano. 70 miles west of Aya is Thringnukugir crater. It's a unique location that gives a tantalizing insight into how Iceland's volcanoes work.
As we go down here, it is quite narrow here. We just make it.
This is really, really neat.
After squeezing through the neck, they're confronted with an amazing sight.
Whoa, look at that.
Yeah, it's beautiful.
A vast chamber, dropping 450 feet below the surface. 4,000 years ago, when the magma drained, the chamber remained remarkably intact. It's the only place on Earth where scientists can study a volcano from the inside.
Really impressive.
Freystein Sigmundsson is looking for evidence of how volcanoes like this are fed by molten rock. It's been something of a mystery until now.
Look at this. Can you see the fracture?
Wow. It's actually really cool how it goes up.
This is absolutely unique place. It is fantastic. We can see the fissures that fed magma into this volcano. This black line in the wall here, it's a crack that delivered magma to the eruption. Now the magma is solidified in this fissure.
This fissure acted like a giant vein, pumping magma into the chamber horizontally, as well as from deep below.
What is so special is we can clearly see it both sides.
The fissure sliced right through the chamber and out the other side, and Freystein is working out which direction it took.
If you trace it, we can get orientation of this crack.
By lining up the fissure on either side of the chamber, the team finds the exact route it took and makes an important discovery.
What we have found out is that they can go on for many miles. They are like thin sheets. They can link different volcanoes.
So although volcanoes appear isolated on the surface, fissures carrying magma can link them underground. And that's an important consideration in trying to predict which of Iceland's volcanoes might erupt next. Historically, Katla has erupted shortly after Ea on more than one occasion, suggesting hidden underground fissures could link them. If so, could Ea's recent 2010 eruption be the trigger that sets off the giant ice-covered Katla again? Or one of her other volcanic neighbors? And what would be the consequences? Volcanoes are some of nature's biggest killers. They threaten us with torrents of molten lava, clouds of choking ash, mists of toxic gas. And in the past, Iceland's inhabitants have suffered more than most. In 1783, an eruption kills over 10,000 locals. It's one of the deadliest ever recorded. A killer that atmospheric scientist Anja Schmidt knows all about. 50 miles northeast of Ea lies the volcano Anja's interested in, the fissure called Laki.
We are standing on the Laki lava flows. So as far as the eye can see, we can see the moss-covered lava flows from the 1783 Laki eruption. Just to give you a feeling for the scale, the area that these lava flows cover is actually 10 times the size of Manhattan.
Why Laki produced so much lava is due to her volcanic character.
Laki has a very special personality. It's very different in terms of eruption style, how it erupts from other volcanoes. It's a so-called fissure eruption, which means it erupts along a linear vent system.
A linear vent system works like this. Instead of erupting from a single crater, lava gushes along a line where the fissure breaches the surface. In the United States, fissure eruptions are common on the big island of Hawaii, like this one in Kilauea. In 1783, Laki also erupted from a fissure, but on a vast scale. The Earth opened up along a 17-mile fissure, spraying molten rock skywards.
Just imagine the Earth's crust zips open along a line. If we were standing here in 1783 witnessing the Laki eruption, it must have been a pretty frightening sight. So the sky would have been black and dark because the first volcanic ashfall will come down. And looking towards the actual eruption site, people could see fire fountains glowing red into the sky, rising up to 1 mile high into the sky. And then you will have these lava flows slowly advancing, so you see incandescent, red glowing lava flows in this darkened landscape.
It sounds like a vision from Dante's Inferno. But surprisingly, it wasn't lava that was the killer. It was something far more lethal. Something that, if repeated in the 21st century, could affect millions around the globe. In the heart of the English countryside lies the disturbing evidence for this possible disaster. Here in church records, forensic geoscientist John Grattan is uncovering clues that revealed just how far Loki's deadly eruption reached.
This is a parish record, and it contains the dates and names of people who've been buried here, which is what I'm particularly interested in. Using books like this, we can reconstruct the patterns of mortality.
Deaths normally occur in winter, when the old and ill succumb to cold weather. But John's uncovered a period of time in 1783 where the records don't appear to make any sense.
We can see an intriguing change to that pattern, where people are dying in significant numbers in the summertime, when the weather is good, when there's plenty of food. So we're interested as to why that might be.
Other accounts describe how the villagers are dying. They read like a horror story.
In the foul hot weather in the beginning of summer, ulcerated mouths and eruptions on the lips, and also pains in the face, became epidemical. Burning fevers were accompanied with pleurisy and inflammation of the lungs. The burning fever and dysentery immediately came on us in the centre of England and became epidemical in London. And there were some remarkable instances of sudden deaths.
The killer's not only devastating the population, it's ravaging across the land.
The barley became brown and weathered at the extremities, as did the leaves of the oats. All the different species of grain appear to have had all their leaves withered, exactly as if a fire had been lighted near them. And the occurrence of a tremendous thunderstorm seems to bring together everybody thinking, this is it, this is the end of the world.
But it isn't just England suffering. Vast areas of Europe experienced the same calamity, as recorded by a founding father living in Paris at the time.
This is what Benjamin Franklin noted. There existed a constant fog over all of Europe. This fog was of a permanent nature, it was dry, and the rays of the sun seemed to have little effect towards dissipating it, as they easily do a moist fog arising from water. And what this tells us is that this fog is not water vapor, it's something completely different.
The killer is acting on a continental scale. The question is, what is it? Edinburgh, capital city of Scotland. In the university labs, geologist Chris Hayward examines lava from Loki. He's looking for chemical clues that might identify Loki's killer.
One of the most interesting things that we can see in these lavas are these very tiny crystals, and what these do is they record the chemistry of the magma at different times in its evolution, from the time when it formed very deep under the ground until it was erupted. So they're like little time capsules.
As the crystals grew, they entombed tiny pockets of Loki's magma inside them, along with its chemistry.
So here is one of the crystals, this dark area, and you can see one of the little pockets of magma, and if I zoom in, this is the thickness of a sheet of how small these things are.
Using a sophisticated electron microprobe, Chris teases out their chemistry and finds something intriguing.
We've discovered something very interesting. The material inside the crystals, these pockets of magma that were trapped early on, contain large amounts of sulfur.
The crystals formed miles underground, when Loki's magma was relatively rich in sulfur. But when Chris analyzes the solidified lava surrounding them, formed much later on during Loki's eruption, he makes a remarkable discovery.
The final magma that froze in the lava when it was erupted contains almost no sulfur at all.
So where did the sulfur go? It escaped from the rising magma as a gas into the air.
We estimate that around 120 million tons of sulfur was released during the eruption.
So could lucky sulfur be responsible for the deaths in Europe and Iceland in 1783? If so, how might it kill? Chemist Andrea Sella has the answer.
Sulfur is actually really very abundant. It's kind of up there in the top 20 elements in the Earth's crust. And native sulfur actually often comes out of the ground in volcanic areas to give this wonderful lemon yellow material.
It also has a very distinctive odor.
If we take a sample of commercial powdered sulfur and take the lid off and give it a quick sniff, it's got a delicate, almost evocative smell. It's something a little bit like a freshly sliced hard-boiled egg. It's the kind of smell that you often get near hot springs or thermal baths, something that you associate with volcanism.
Throughout history, sulfur's long been associated with boiling mud, volcanoes, and hell.
It was brimstone, the devil. It was clearly a dangerous and powerful substance. And in order to show this, what I think we should do is to heat a little bit of sulfur up and see the incredible things that it does. As we warm it, it soon begins to melt. We're gradually getting this deep, dark liquid. This is a little bit like traveling ever deeper into the bowels of the Earth. And if we go down far enough, deep down in the magma, the temperatures are so high, the sulfur is actually transformed to a gas.
And as the magma rises, the gas escapes explosively as sulfur dioxide.
This is among the most dangerous stuff that a volcano can produce.
Climate scientist Mike Rampino understands the threat from sulfur dioxide only too well. He's come to one of Iceland's major attractions, the thermal pools at Geyser, where water is volcanically heated in spectacular fashion.
We're sitting in front of a hot pool which is giving off water vapor and steam. But I can also smell and even taste acrid gas, and that's the big problem with volcanoes, the amount of sulfur gases that they release into the atmosphere.
The sulfur dioxide gas given off by these pools is nasty enough. But when it's pushed into the atmosphere during an eruption, it can become a far more lethal chemical compound.
The problem is that when the sulfur dioxide reacts with water vapor, it forms a little droplet of the acid sulfuric acid. And so up in the upper atmosphere, if enough sulfur is released by the volcano, you get this mist of sulfuric acid droplets.
It's the same acid found in your car battery, and it's dangerous stuff.
Sulfuric acid at lab strength is a really, really potent acid. In fact, it's really something of a tiger. And if we were to take some flesh, a piece of meat like this, and then we can take some concentrated sulfuric acid and pour it on top, the results are going to be really unpleasant.
Andrea's using concentrated sulfuric acid to show the grisly effects it has on tissue.
Within seconds, you start to see changes in the color and the surface of the flesh. And you can see it going from that happy dark red color to something much more sort of beigey brown. So what the acid does is it actually reacts with the protein in the flesh. It's a little bit like cooking. What we've done, in effect, is that we've used the acid as a kind of tenderizer. Wow, look at this. Here we've got some meat which has been in the acid for about 10 minutes. Whoa. And really, we can now pull it apart. What we're ending up with is something truly horrific.
Sulfuric acid formed from volcanoes is far more dilute, forming fine mists. Even so, it's something you wouldn't want to breathe.
Your lungs have some very, very delicate exposed tissue. They haven't got skin over the top. And the result is that anyone inhaling this mist is going to initially suffer some quite serious irritation. But there's going to be very, very long-term cumulative damage if this goes on for any period of time.
In 1783, Loki's fissure eruption lasted for 8 months. Iceland's inhabitants didn't stand a chance against Loki's acidic cloud. And this cloud also killed hundreds of thousands more in Europe, according to John Grattan. But how could an eruption in Iceland affect people across such a vast area so far away?
How on earth can these gases be concentrated sufficiently that you can taste them and smell them, that they'll burn your eyes over 1,000 miles away?
The answer to that lies not with Loki's eruption, but with the weather. During the last week of June 1783, high pressure sweeps over northwest Europe, bringing fine summer weather. But it also allows something foul, high in the atmosphere, to sink downwards.
That's where the volcanic gases are. Now they're being sucked down, dragged down to the Earth's surface, and it's like a blowtorch devastating the environment below it.
The high pressure acts like a vast funnel. Air spiraling down from the upper atmosphere brings with it Loki's poisonous gases.
If we were standing here in 1783, the view behind us would have disappeared. What we would see instead would be a blue haze across the landscape. The colour green would disappear because the acids burned into the trees. The crops would have been burned. People dying, the birds dying, the fish floating to the top of the ponds because they've been killed as well. Really, a view of Armageddon.
It's the final link in the chain of events that triggers a volcanic catastrophe over Europe.
One thing we do know from the geological record, that events that have happened in the past will happen in the future. So these events of 1783, they will be repeated again.
What nightmare scenario awaits us if that happens? If Loki's cloud reached Europe in 1783, how far could one stretch today? Anja Schmidt has taken Loki's sulfur output from the 1783 eruption and, using a computer model, ejects it into today's atmosphere. It's a disturbing picture.
So the eruption starts in Iceland, and then, as you can see in the model, the sulfurous cloud spreads across Britain, Germany, France, and Spain. It's not only affecting Europe, but also into North America. So over the course of 8 months, the entire northern hemisphere is filled with a sulfurous cloud from one eruption in Iceland.
So how could that affect us? Already, many cities generate pollution that causes premature deaths from asthma, heart, and lung disease. Could a toxic cloud from Iceland prove to be the tipping point? Combining today's pollution with Loki's 1783 pollution, Anya estimates the extra deaths if the same volcanic acid cloud swept over Europe today.
Using our model, we can create a kill map. What we find is tens of thousands of deaths in the UK, in the Netherlands, in Germany, in France, all over Central and Western Europe. If we calculate the total, we find a mortality rate of more than 100,000 people. This is quite an astonishing number.
Since her model shows that the cloud would eventually spread across the entire hemisphere, it's a stark warning of what we might expect in American cities. But there's another threat from Iceland's volcanoes. 45 miles west of Laki is Hekla. At almost 5,000 feet, Hekla's distinctive cone towers above the landscape. She's one of Iceland's most active volcanoes, erupting over 20 times in the last 1,000 years. Hekla last erupted in 2000, and recently, her eruptions have been mild. But Thor's discovered a place that shows just how explosive she can be. And with Hekla, it's all about ash.
The snow-covered mountain in the background there is the Hekla volcano itself. And here in the foreground, this light-colored layer there at the top was erupted from Hekla 3,000 years ago.
These ash layers tell Thor a great deal about Hekla's explosive past.
The reason why we spend our time studying these ash layers is that we can get information about the nature of the eruption, its intensity, its explosive power, and how widely it affected the environment.
He's discovered one particular eruption from Hekla 3,000 years ago, which threw out a tremendous amount of ash.
If you look at the landscape around us, all the surface is covered with the ash, which is 15 feet thick. And it doesn't matter where you look, it's all around you. That gives you a good indication of how powerful, how strong that eruption was.
Hekla's explosive eruptions created this barren landscape. It's made of layer upon layer of ash, formed from pulverized magma. And it's typical of Hekla's family of volcanoes, the stratovolcanoes.
Most stratovolcanoes around the world will produce big explosive eruptions. Every so often, we have the Big Bang.
Now we've got an eruption down here.
It's exactly what happened in Washington State in May 1980. Mount St. Helens, America's most famous stratovolcano, erupts. Rising magma triggers an earthquake and a vast landslide.
The whole northwest section blown up. I'm going to back out of here. It's down.
Sending ash 80,000 feet high in just 15 minutes.
This is as far east as you can go.
And causing over 50 deaths.
I can't believe it. Doesn't look like any place I've ever been before.
Europe's most famous stratovolcano is Mount Vesuvius. When it erupted 2,000 years ago, gases and hot ashes rained down on the towns of Pompeii and Herculaneum, asphyxiating an unsuspecting population and killing up to 25,000 people. But what Thor's discovered about Hekla's eruption 3,000 years ago makes Mount St. Helens, Mount Vesuvius, and Aya's 2010 eruption pale in significance.
We've learned that this is one of the biggest eruptions from Hekla in the last 10,000 years. And the total volume of this material is between 2 and 3 cubic miles. It also sent ash plumes extending from Greenland well into mainland Europe. If we were standing exactly in this location 3,000 years ago when Hekla erupted, the first thing we would have seen is a humongous column of ash rising up from the volcano, and from that plume you would have ash raining out, and along with that you would have blocks like this one here flying through the air. This one is 20 pounds, so this eruption, it would have killed you and you would have been buried in 15 feet of ash.
When Ea erupted, her ash grounded aircraft for almost a week. But Hekla could be far more disruptive. 3,000 years ago, Hekla produced 75 times more ash. The concern is she might be about to do it again.
The pattern that we have detected is suggesting that right now it is at the end of a phase where eruptions are diminishing in size, indicating that we might be entering a new phase, which usually starts with a big explosive eruption. So it's possible that Hekla might produce a very big explosive eruption in the near future.
What chaos might we expect if this happens? Claire Withram has been asking the same question. She's part of a rapid response team at the London Volcanic Ash Advisory Centre at the UK's Met Office. It's the first line of defense against volcanic ash for Europe's aviation industry. And went through their paces.
We hadn't seen anything that had really blown an ash cloud from Iceland to our area in recent history, so it hadn't really got into people's minds that that might happen. The Eyjafjallajökull eruption went on for about 39 days. People were working around the clock here on a scale that we hadn't really experienced before.
The minute an eruption occurs, observers in Iceland contact the team.
We then have a race against time to get out an advisory. We then have to update that information every 6 hours until the end of the eruption.
Claire needs two key things to predict where the ash cloud is going. First, she needs an accurate weather forecast.
The weather's really vital because when the ash is erupted into the atmosphere, it then gets transported by the winds at those higher levels and gets taken wherever those winds are going.
How forcefully the volcano erupted is also critical.
We need to know how high the eruption is and also how much has been emitted and how that changes with time.
Armed with this information in 2010, Claire and her team used supercomputers to model the movement of ash from Ea.
So what we can see is the start of the eruption, and then the ash is transported to the southeast and is then dispersed across the northern hemisphere.
In the future, with the possibility of bigger eruptions, the team's predictions will be even more important. To see what might happen, Nova asks Claire to make a model using Hekla's huge eruption 3,000 years ago, which belched up to 3 cubic miles of ash, and the weather conditions when Ea erupted in 2010.
So this simulation shows the first ever model run of a much larger eruption. And what we can see is that because this eruption was much bigger, so it went much higher in the atmosphere and produced considerably larger amounts of ash, the plume covers a much wider area and the levels of ash in the plume are much greater, which is shown by this red colour, spreading out over a much larger region of Europe and also across the northern hemisphere. And what this tells us is that for a future eruption of a larger size, the potential for disruption is greater.
What's worse is that we might not have time to prepare.
Hekla does not give us much warning. Her temperament is such that she will flare up 30 minutes before it erupts, so she can surprise us.
As scientists are learning, Iceland's home to a group of deadly volcanoes. Ea blew in 2010. Laki sent a toxic cloud of sulfur circling around the northern hemisphere. And Hekla which could unleash millions of tons of ash without warning. But the greatest threat is from their restless neighbor.
I would be more worried about a Katla-style eruption happening today.
One that volcanologists can't afford to ignore.
The concern of Katla is that it might erupt anytime.
The volcano, hidden under the ice.
Katla is rumbling.
Some fear her eruption could be worse than Laki's sulfur cloud and Hekla's ash put together. Katla erupts every 50 years on average. Her last major outburst was nearly 100 years ago, so an eruption is long overdue.
All the signs that we detect from the volcano are telling us that it is building up to an eruption.
Recently, scientists have detected swarms of earthquakes around her crater. Whether this threatening activity is because Ea's eruption has lit Katla's fuse, no one knows. To find out what's going on, Sigrun Herensdottir and Freystein Sigmundsson are making the 3-hour trip to the volcano's summit to set up monitoring stations.
We are driving now up to the glacier, and we need a guide because it's a fairly rough environment and there are crevasses to worry about.
It's a treacherous journey. Katla's crater is over 6 miles wide, buried below the ice. Sigrun is looking for a specific site to set up one of her stations, somewhere where Katla's rim breaks through the ice.
Right on the top of the bedrock there. Yeah, it's actually, the bedrock is the caldera rim sticking right out of the glacier.
Yeah, what a fantastic sight.
It's the perfect spot. This rocky outcrop connects to Katla's magma chamber deep below. If the magma moves down there, so should the ground above it, here.
This is just a simple antenna that is receiving data from the satellites that are traveling across the sky. And we hook the antenna to a receiver, and the receiver is logging the data.
The satellites transmit signals to Sigrun's GPS network, stationed around Katla's rim, providing an extremely accurate fix on their positions. If Katla's magma chamber inflates, its rim pushes outwards, moving the receivers. Even a tiny shift of less than 1/8 of an inch can be detected.
129.3.
So magma, like molten rock, is coming from great depth into the volcano, and what we have is like a magma chamber, which is just like a balloon. If you imagine you put air in a balloon and it inflates, we can actually sense that on the surface.
And there are indications that Katla's chamber is indeed inflating.
So first, we can actually look at the data from the GPS station that is right here at Katla volcano. Yeah. And we set this up during the Eyjafjallajökull eruption. This is 2010, and now we are in 2012. And you can see that the overall trend here, that is up. So like inflation of the magma chamber is almost 8 centimeters. It's quite a bit. The magma chamber of Katla volcano is inflating.
The GPS readings show Katla could be building to an eruption. So what's the worst we can expect from her? Thor's been investigating layers of black ash the volcano ejected in 934. What he's uncovering alarms him.
So here we have the lower part of the deposit. It is the bottom, and it's fairly coarse-grained. This is the one thing that we really want to worry about. Explosive events like this produce a lot of ash.
Volcanologists have measured the thickness and extent of these ash layers, allowing them to calculate the volume of material Katla erupted 1,000 years ago.
The results tell us
This eruption at Katla, in terms of volume of material, is double the Hekla eruption 3,000 years ago.
The closest we've come to experiencing an eruption on that scale rocked the Philippines in 1991, when Mount Pinatubo erupted. This, one of the largest eruptions in modern history, rumbled for just over a week, sending an estimated 2.5 cubic miles of ash into the atmosphere. But Katla's ash reveals she can erupt for far longer.
There are many, many, many layers there, which means that this eruption featured many, many explosive events. It's a complex eruption and probably lasted for at least 1 year.
If a year-long eruption of ash wasn't threatening enough, Katla also spewed 220 million tons of sulfur, much more than Laki in 1783.
It is double that of Laki. So it is the biggest eruption in Icelandic history, and it is the biggest volcanic pollutant in recent times on planet Earth.
It's this acidic pollution that scientists fear the most. If Katla erupts today, the devastation could trump the effects of Ea, Laki, and Hekla combined. And the amount of sulfur produced would be far worse.
Well, sulfur has a sort of a double whammy effect when it's in the atmosphere. The little droplets of sulfuric acid, or aerosol as it's called, stay in the upper atmosphere and cut out some of the sunlight that would come in and warm the Earth. So the result is that the Earth gets cooler.
Katla has the power to change the world's climate.
A long-duration eruption such as Katla, if it happened today, would cause quite a mess on a global scale. The numbers are about 2 degrees Celsius cooler. It doesn't sound like much, but it's enough to cause a transformation of the landscape.
The evidence is clear. Iceland's volcanic eruptions could have global consequences, producing enough ash and sulfur to change the world's climate. But could we protect our economy if a less powerful eruption, like Ea in 2010, occurs in the near future? It's a vital question for the airline industry, as aircraft will be the first to feel the effects. At 35,000 feet, ash particles are so fine, they are invisible to the naked eye. So when Ea erupted, thousands of planes were immediately grounded. It's a problem aircraft engineer Ian Davies has been grappling with.
Well, we know ash and engines don't mix because this modern turbofan engine behind me basically takes in hundreds of cubic meters of air every second.
Any volcanic ash sucked into the engine, which heats up to 2,000 degrees Fahrenheit, melts and sticks to vital parts.
And when it does that, it will cause a surge stall, which is effectively a backfire. And in doing so, we can get flames out the front and out the back of the engine. And ultimately, it will shut down.
Fred Prada, an imaging expert, is developing a unique system that could help. It's called Avoid.
This instrument here is a fast sampling dual camera system measuring in the infrared. Infrared radiation is heat. Every molecule in the atmosphere that's vibrating emits infrared radiation.
Ash particles also emit infrared radiation at a particular wavelength.
Now, they have a particular spectral signature in the infrared, which is quite different to that of other things in the atmosphere, like water clouds, ice clouds, water vapor.
The cameras, which can pick up infrared signatures, provide pilots with a picture of the sky up to 60 miles ahead. allowing them to distinguish between ash and clouds.
So now he can start to see where the ash is. If it is there, and he sees it 5 or 6 minutes ahead of time, he can then make a small deviation and avoid it completely, safely and economically, and land his aircraft.
The new system could be the first step towards keeping planes in the air when ash next rises from Iceland. And it could help pilots map and maneuver around invisible ash clouds while they're flying, even reducing the need to ground planes. Still, the greatest threat would come not from Katla's ash, but from her toxic sulfuric acid cloud. Faced with a giant volcanic eruption today, a major response would be needed to protect us.
But how would they do that? They do that by switching off the power stations that might be burning coal. They do that by stopping us driving our cars that are emitting pollution from the engines. They do that by closing factories down.
I think modern day society should very much be concerned with volcanism.
I think we're probably more susceptible to these types of events in the 21st century than we were even in the early 20th century.
We think we're immune to these things, and frankly, we're not.
Those least able to protect themselves would be most affected.
To be brutal about it, the vulnerable population will be culled from society. The elderly, the sick, people with heart and lung conditions, the obese. We're going to see many, many people dying.
Today, we have a society dependent on air travel.
The way we move food, freight, people around the world now, any disruption to that is devastating.
A society that's delicately linked together.
So a massive volcanic eruption is really going to disrupt this web of connectivity. All those networks are going to be fractured. They're not going to work anymore.
Lives were thrown into chaos when Ea, a relatively small volcano, awoke in 2010. How much worse will it be if and when one of Iceland's doomsday volcanoes erupts again?
Major funding for NOVA is provided by the David H. Koch Fund for Science, supporting NOVA and promoting public understanding of science. And by the Corporation for Public Broadcasting. And by contributions to your PBS station from viewers like you. Thank you. Additional funding is provided by Millicent Bell through the Millicent and Eugene Bell Foundation.